Yeah, so I'm going to talk about CBAS. First of all, apologies for not being Angela Taylor. She's indisposed today. Right, so okay, so there is Angela, along with actually a quite old photo of the CBAS team. Despite the reasonable number of names on this slide, CBAS is actually a pretty small collaboration at the moment, with the active people sort of listed at the top there. So I'll talk about briefly what CBAS is, but quickly. So here's pictures of it. It's 2 telescopes in the northern and southern hemisphere. CBAS North up here at Owens Valley. We've just been hearing from data from Owens Valley in California, and here in South Africa, close to the SKA site, and we're in Oxford here, roughly halfway between the two. So the sort of vital statistics of CBAS. So it's an all-sky survey, but it's all-sky in 2 parts. So the northern survey actually covers north of declination -16. The southern will be south of +29, so that telescope's a little bit closer to the equator, with an angular resolution of 45 arc minutes. The sensitivity we're aiming for is essentially that it's confusion limited in I and sensitive enough to detect polarized synchrotron across the whole sky in Q and U. So the sensitivity, if in usual CMB units, is about 6,000 milli-K arc minute at 5 gigahertz, which sounds a bit crazy if you're used to sort of typical CMB sensitivity numbers. But the point is that if you extrapolate from 5 gigahertz to 100 gigahertz with a typical synchrotron spectral index, that's equivalent to a sensitivity of 0.75 milli-K arc minute. So in terms of sensitivity to synchrotron at a level that matters for the CMB, CBAS is very sensitive indeed. And we get IQU nominally V, but in fact, we never look at V. And it's sensitive at 5 gigahertz, again, nominally a gigahertz bandwidth, but actually after various RFIs taken out, it's about a half gigahertz that's left. So the sort of unique features of CBAS, it's the only all-sky experiment at this particular frequency, and the frequency was carefully chosen. It's high enough that Faraday rotation is not an issue. So if you compare, for example, SPAS, just only a factor of 2 lower in frequency, has a much bigger problem with Faraday rotation, and it's low enough that the synchrotron is still very bright. So compared, for example, say to Quixote, which is another factor of 2 or 3 higher in frequency, again, where that declining spectrum means that the synchrotron is a lot less bright. So we think it's very well optimized for measuring galactic synchrotron. It has a very well characterized beam. So we'll look at the antenna again in more detail in a moment, but the aperture is blocked, but only by a single circular obstruction, which means that we can simulate the beam quite accurately. We verified the simulations by measurement. So we understand our beam. We have no real problem with missing power in far outside lobes, which means that the temperature scale is well characterized, and that we measure intensity and polarization and calibrate them together, so that our polarization amplitude scale is linked to our intensity amplitude scale. So we have a direct, well calibrated polarization scale. And we'll see in a moment, the receiver design will look pretty familiar to anyone who's worked on LFI data, but with a couple of small differences. So the radio operates on circular polarization, not linear, which actually means it's better optimized for extracting polarized data. We get QU directly rather than behind the difference 2 channels. And we have the 2 phase switches in the channel, but we operate both of them. So we have a 4-state switching system, which is slightly better at removing some systematics. So here is the CBAS North telescope at Owens Valley. As you can see, it's it's a Gregorian optics with a concave secondary. it has these baffles around both the secondary and the primary, which are there to limit side lobes. The secondary mirror is supported on this block of foam, which is attached directly to the feed. So we have no struts supporting the secondary. It's the next best thing to an unblocked aperture telescope. We would rather have had an unblocked aperture telescope, but we didn't have one available. This really reduces the scattering in the optics, and the entire receiver system is sat behind the feed here, forward of the dish. Actually, essentially all the important electronics are mounted in this structure here. This is CBAS South. It's a similar size, slightly bigger antenna, slightly different optics, and the receiver is a bit different as well. But I'm not really going to talk about CBAS South because all the data we have and we're analysing at the moment is from CBAS North. But CBAS South will complete the survey. So this is the front end part of the receiver. So it's a pseudo-correlation receiver with 2 temperature stabilized loads, 2 orthogonal polarizations from the feed, hybrids, LNAs, and then further gain and processing. We have a noise diode, which we inject into these 2 signals, which is very important for our calibration. And we have this component which sits behind the OMT, which converts linear to circular. So we're all operating on circular polarization from here on. And this is what the back end looks like. The things to focus on in here is that, so at the top and the bottom of this slide, we have the intensity channels. So we take the right circular and the left circular, they go through phase switches, hybrid, power detection. We essentially we demodulate and integrate in real time. So we don't have, well, we have access to a version of the individual sky and load data, but we don't use that for science. We take the data which is already different than integrated before we read it out and store it. And the reason that we do that is because the symmetrical design of the architecture and the full phase switching means that it's actually very good at self-subtracting systematics. So the differencing process that we do produces very clean data already, and it's not worth the overhead of having to read out the individual sky and load channels. We'd have to read them at a much higher time resolution to be able to do essentially the combination offline. And so we have identical for the other circular polarization. For polarization, we just recover the sky signal, dump the load signal, which isn't needed for the polarization measurement, and then do a complex multiply between right and left, which is also implemented with hybrids and diodes, just haven't shown that. And so we have a direct complex multiplication of right and left gives you Q plus IU. And in fact, the internal symmetry of that multiply gives us 2 copies of Q and U, which ought to be identical. And so comparing those gives us a cross check on other systematics as well. So we scan, we do constant elevation scans. Like the primary scan is to go through the North Celestial Pole, which is elevation 37 from Owens Valley. That allows us to return to the same point on the sky every scan, but gives pretty uneven sky coverage. So we also use a series of higher elevations above the pole, which fills in the middle declinations with better sensitivity. And so you can see the kind of scans that you get from a few hours data, either going through the pole or here's 10 degrees off the pole. And over the whole survey, that stacks up into a kind of coverage which looks rather like this. And we scan at slightly different speeds, almost as fast as we can go, but slightly different. So we don't always have a one-to-one mapping between scan speed and angular scale on the sky. We sort of, that helps blur out any residual systematics. So the calibration is based on this noise diode. By injecting this into right and left, it appears in I and Q. And then we essentially compare the apparent brightness of the noise diode with tau A, and that gives us a scaling given the flux density of tau A. But because the Q and U is essentially measured through the same system and the noise diode appears fully in Q, this calibrates both the intensity and polarization channels at the same time. And so we have a direct measurement of the polarization amplitude of tau A, which turns out at our frequency, at our resolution, turns out to be almost exactly 5%. And we can also, we do long observations of principally of tau A, obviously because it's the best polarization calibrator, some lower polarization sources as well. And so by doing a long observation of tau A and watching the sky rotation, we can watch the apparent movement of Q and IQ and U, and that allows us to derive the telescope response matrix which maps observed IQU to true sky IQU. And what we find is that there is actually a mixing between Q and U that's not just a pure rotation, which varies between a few and a maximum 10%, which we calibrate out. And the I into QU leakage, because of the switching effects in the polarimeter, is measurable, but it's much less than 1%. And then the polarization angle, we don't do an intrinsic polarization angle calculation ourselves. We take the results derived by the WMAP group from this paper. And then we convert our flux density scaled data into brightness temperature using the beam model, which I said we have quite accurate beam model. So the effect of the QU calibration is, if we start off with, for example, some raw data, which are these red dots, this is plotting Q and U as we observe tau A over 12 hours, or a little bit less than 12 hours. And then essentially we find the calibration which forces these red points to go onto a circle, so that we're now, we've got polarization angle being accurately measured. The main systematics and challenges in the data, RFI is a problem. I'll show you some RFI pictures in a moment. The worst things actually in data reduction obviously is the sporadic RFI, which is mostly from airborne radars. There's also ground-based fixed RFI, which is mostly constant, but does turn on and off as well. Ground pickup is almost our biggest problem. Despite the good beam response of the antenna, we do pick up the ground, and that is a big systematic. And because of our scan strategy, fundamentally there is a degeneracy between a feature in the sky which looks like a ring of constant brightness around the North Celestial Pole, and a feature on the ground. And so we can suppress that signal as much as we can, but there always is an ambiguity, which in the end can only be broken by independent observations there. We also have a microphonic signal, which is picked up in the electronics, driven by the mechanical signal from the cold head, which is a pain. And also a problem which is unusual in CMB observations is that a lot of our data are actually signal dominated. So we get instantaneous signal to noise, or looking at any kind of galaxy of many in milliseconds. So we have to subtract a sky model to get our data down to being roughly noise-like before we can do many other operations. And so that drives us into a sort of an iterative processing where we have to make an interim sky model, use that, process our data, improve the map, and so on. So just to see what the immediate RFI sort of environment looked like, this was a very early image that we made just by scanning the telescope in azimuth and elevation, and this is what groundsville looks like in 2D. So there is a signal which is corresponding to that mountain there. We have radio transmitters on the horizon, really quite strong here, and then we have geostationary satellites. And then we can obviously see things in the sky as well. So we had to actually make quite a lot of hardware changes before we could get good data. So this was our first iteration of the receiver, and you can see how this actually is an in-band transmitter. And we had to install in-band filters to get rid of this, and these satellites are out of band, but they're incredibly strong. So we had to install additional out-of-band filtering before we ended up with this data which is as clean as this, but even so, as you can see, the ground spill is always going to be visible when you're tracking at moderate elevations. The receiver itself, obviously the pseudo correlation architecture gives you pretty good stabilization. So this is our raw 1/f noise power spectrum in black, and then in red is what we get after the sky lobe subtraction. It's not perfect because it's hard to balance the receiver perfectly with the same intensity in the sky and reference channels. But then the QU channels, because it's correlation between different channels, has very, very low intrinsic 1/f noise. And so our scan period is, say it's about 100th of a hertz. So we have some residual 1/f in the intensity and really not very much in the polarization. So I said, yeah, the beam is, the quality of the beam is quite important. So this plot here shows actually 3 different sources extracted from our survey. So Virgo A, M42 and Tau A, along with our beam model. And so going down to nearly 30 dBs down the beam, we're following the beam pretty accurately. And so if we then take our beam model and integrate it, so this is a slightly weird linear y log x scale. So you can see here is our beam shape, first side lobe, and then side lobes go down very quickly. And the integrated beam has converged essentially by 10 degrees. So there's less than 1% of power in the beam outside of 10 degrees. So we really don't have when it comes to doing the calibration, we don't have to worry about power on very large scales. Though we do have to worry about correcting the flux scale essentially on these scales between the beam size and 10 degrees. So a bit of raw data. So this is a 2-hour schedule, as we call it, with a couple of sky dips at the beginning and middle and end. And here you can see something has turned on and is being seen every scan. And so we have to take our sky model. So this is the model generated from a current version of the map. We subtract that from the data and then essentially do a clipping process where we would then monitor the skewness and kurtosis of the residuals and try and get those below some reasonable limit. And if we have to keep on clipping so far that we eventually say lose half the data in scan, then we just throw away everything else. So the ground is a big systematic. So this is what the ground profiles look like in each of our channels. So the 2 intensity channels and then these 2 copies of the Q and U channels. And so each color here is the profile extracted from 1 2-hour schedule. And then the black line is that averaged actually over plus or minus a day from that schedule. And so you can see that this is sort of typically good data. I would say there's some horrible data which we obviously don't use, but we can generate these profiles which we then subtract from the data. And this is those profiles now essentially over the whole period of the survey, which is about 2 years. And so you can see that the broad features are pretty constant because those are the mountains surrounding us. But there's quite a lot of fluctuation on moderately short timescales, just due to changes in weather and moisture in the ground and so on. So we do have to track the ground at say at roughly the day level to track the fluctuations. And so this is actually our ground removal process, and I won't go through it. But the point about this is that we want to end up with having been able to subtract a sky model which has itself been ground subtracted from our data before we make our final ground profiles. So that actually involves a 3-stage sort of loop, so that we aren't, or we're doing our very best not to imprint structure that's actually integrated structure from the sky signal into our ground profiles, and therefore introducing these artifacts into our maps. The 1.2 hertz microphonics is also a big signal. So this shows just a few seconds worth of data, and this cycle, as you can see, is way bigger than the instantaneous noise in our data. And this is due to the mechanical pulse of the cold head, which is rattling the receiver, and there are some microphonics which we've never managed to fully eliminate in the receiver that actually couple that into the signal. And so because this is driven by this mechanical motor, which is driven by the mains, it goes with the mains frequency. Now, the mains frequency in the US obviously is 60 hertz, but it's not exactly 60 hertz. And it drifts on short time scales as the load on the grid changes. And the power utility basically keeps it within limits of a fixed frequency and phase. But it does drift on short time scales, and it drifts enough that we can't just integrate this signal on a known fixed frequency. So we have to break our data into small chunks, and essentially within each chunk identify the frequency and phase and waveform of the signal and subtract that, and then do that iteratively, so until we get the power close to this signal down to an acceptable level. So this plot shows here in blue the power spectrum of a chunk of time ordered data before the subtraction. You can see this whopping great spike at 1.2 and 2.4 hertz. And then after we've gone through this iterative process, we've got the green, which is, we haven't notched this out. There's still, we hope, signal power at this frequency, but we've got rid of most of the spurious signal. Skipped over that. Okay, so after all that, we map. This is this is actually a slightly old version of the map. We're just working on, we sincerely hope, our final versions of the maps at the moment. Although these maps I think look very nice, there are some low-level systematics in these which we've been struggling to deal with, basically associated with these last few effects I've been talking about, the 1.2 hertz and the ground subtraction. But nevertheless, that's I think a nice map, and the cumulative signal to noise plot here is quite nice. So basically, there are no pixels in intensity that are detected at less than 20 sigma, and most of the sky is detected at hundreds of sigma signal to noise. Obviously, in the IMAP, we have no information on the monopole from our data. So to try and fit the monopole, so we have maps with zero levels, we trust, we're actually using the arcade data. So these are the maps made by Arcade, which did this little circle crossing the galactic plane, and so essentially we fit a power law through the lower frequency Arcade data, and then find the offset that we have to add to CBAS map to best put it onto that line. Having subtracted the dipole as well helps. And we discover actually that the offset that we need is significantly greater than what we'd expect for the just from the integrated source counts of extragalactic point sources. So there probably is some very, very large scale diffuse galactic emission here, which is adding to our overall signal level. Again, this is a slightly old version of the polarization map, still with a few artifacts in it, but again, just to show you kind of what the data looks like. So that's polarized intensity and angle. Again, as you can see, we have very good signal to noise over most of the sky. So there's only a few percent of the sky with less than 5 sigma detection, and again, we're typically detecting polarized intensity at many tens of sigma over the whole sky. And just to show you the sort of comparison with how much this improves our map of the synchrotron. These are same resolution maps of polarization angle from CBAS, and then WMAP and Planck. And obviously, polarization angle is quite sensitive to the noise level. So this is to show CBAS in the best light. But as you can see, yeah, the signal to noise that we're getting on the synchrotron is very much higher than what we currently have available. So although we have shown sort of some preliminary science results at previous meetings, because we're actually now just working on our hopefully final to be released version of the data, I'm not going to show anything of that because we're getting final versions of that ready now. So the plan is that we're now trying to write up the northern data in the very near future. I think we finally ironed out all the bugs in the pipeline. We will release the data, reasonably soon after the papers come out. But we are still very keen to collaborate with people who have got relevant other data sets that we can work together on. I think it will be much more useful to if people want to use the CBAS data to talk to us rather than just taking sort of blindly what we're able to put out. The Southern Survey, unfortunately, during COVID, we've really not been able to do any work in South Africa at all. So that is essentially in suspension for the moment. We haven't finished taking data in the South, and we haven't taken any data for over a year now. And the data that we will release, we're certainly planning to obviously release maps, beams, source catalog, source subtracted maps. We don't have the effort to support releasing and supporting time order data. Again, if there's anybody has a great idea where they think we could do something fundamentally better at the time order data level, that's something we can talk about, but probably not planning on releasing that. Okay, and that's me done. Thanks.